In this video, we're going to find the equation of motion of the following system, and we're going to find also the solution to that equation of motion, as illustrated in figure 2.5. So this system initially is in static equilibrium. Mass 2 is hanging there, but it's not exerting any forces between the spring and mass 1. And eventually, the system is going to start moving when mass 2 is dropped at a distant h. It will collide with M1, and they're going to be attached together. There will be no rebound. They will remain attached together, and they're going to be vibrating. So I'm going to show first a free body diagram in the static equilibrium position to show that the forces, the sum of forces are equal to 0 because there's no movement. So therefore the forces counterbalance each other. And then I'm going to show a free body diagram of the vibrating system and a sum of forces for that system. I wanted to start with the static equilibrium position to show why the forces will cancel out later on when we are analyzing the system in movement, and we don't need to consider those original forces when we analyze the system after static equilibrium position. So I'm going to explain this better with the drawing. So in the static equilibrium position, I can see that let's draw a free body diagram. So the free body diagram will be mass 1 connected to a spring force Fs and the weight of mass 1, which is equal to m1g. As I said before, the acceleration is equal to 0, so sum of forces is equal to mass by acceleration is equal to 0, and sum of forces is equal to minus Fs. Let's say the direction of movement is positive downward. So minus Fs plus m1g is equal to 0. And from here we can see that Fs is equal to m1g. So these forces are equal, therefore there's no movement. So let's say this is equation 1. Now let's analyze the system after mass 1 was dropped at a distant h, and that when it collides to mass 2 was dropped at a distant h, collide with mass 1, and the system start moving. So moving system, we can say that now, or vibrating system, we can say now that the free body diagram looks like this. This is M2 collides with M1. Now the total mass of this system equals M1 plus M2. And the forces acting on this system will be the spring force related to the stretch of the spring when it undergoes movement downward. So that is equal to kx, and x represents the distance from static equilibrium position downward. Okay, now we also have the mass m2g, which is an additional mass. And just for illustration, we can show that the original forces, if we put it here, Fs and m1g, the weight, will cancel out in this equation. So now, sum of forces is equal to mass by the acceleration in the x direction. So in this system, sum of forces will look like this. Sum of forces equals mass, in this case mass is m1 plus m2 x double dot, and that is equal to the fs negative fx plus m1g plus m2g. The spring forces are negative because they are going upward, and the movement, we already said that going downward will be positive. Now, if you can see, minus fs plus m1g will cancel out because fs is equal to m1g. So this is going to be equal to 0. Therefore, for future problems, we can start analyzing the problems. If we start analyzing the problems from a static equilibrium position, we don't need to consider these forces. So now our equation of motion will be on the following form. Minus fx plus m2g. But minus fx, which is the spring force, at the same time is equal to minus kx plus m2g. So this is our differential equation representing the motion of this system. Now, a second order differential equation like this one will have a total solution which is composed of a homogeneous solution and a particular solution. This is the homogeneous solution and this is the particular solution. So we need to find these two solutions in order to get the total solution of this differential equation. So let's start with the particular solution. To get the particular solution to this equation, we just can simply rewrite this equation by saying that we're going to use only the particular solution, kx particular plus m2g. We can also rewrite this a little bit more by saying that we move these to the left equal to m2g. So now, because this equation, differential equation, is equal to a constant, we can assume that we're going to have a solution that looks like this. X is equal to a constant. So if x is equal to a constant, x dot is going to be equal to 0, and the x double dot, the acceleration, is going to be equal to 0. If we substitute these values on this equation, we're going to see that we're going to get the following. From these, we can find the particular solution. So we can see that kxp is equal to m2g, therefore sp is equal m2g over k. And this is our particular solution for this problem. Now, we need to find the homogeneous solution of this problem now. To get the homogeneous solution, we first are going to find what is the natural frequency of this system. So going back to our original equation, I'm going to write this over here. Now, I'm going to rewrite our original differential equation over here. m1 plus m2 by the acceleration plus kx is equal to m2g. That was our equation of motion, or differential equation that described this system. So what I want to do to find the homogeneous solution, I wanted to set this equation equals to 0. So if we remember from the differential equation course, we learned that to get an homogeneous solution of a differential equation, we will set that differential equation equal to 0. And we're also going to use the standard form of the equation. So I'm going to put this in the standard form, leaving the acceleration alone here, and rewrite the equation like this, equals to 0. Now, let's compare this equation to the characteristic equation of a free vibrating system with no damping. So that equation, that characteristic equation, is of the following form. If we notice, to get W, we just have to equate W squared to the coefficient of X, and that will give us the natural frequency of the system. So let's do that. W squared is equal to K over M1 plus M2, and then W will be equal to the square root of K over M1 plus M2. So we now have the value of the natural frequency. Now, let's notice that the homogeneous solution of this equation looks like this. So it's A sine WT plus B cosine WT. In order to find this homogeneous solution, we need to find constants A and B. So in order to find these constants, we need to know the initial conditions of the system and apply to the total solution so we can get the constants A and B. Let's notice that, as we discussed here, the total solution of this system is a combination of the homogeneous and the particular solution. So now I'm going to write that term for total solution. It will be A sine WT plus B cosine WT plus the particular solution, which we already determined was M2G over K. So this is the equation for the total solution. Now, let's identify our initial conditions. Our initial conditions, we can easily notice that the initial displacement at time 0 equals to 0 because we're starting from a static equilibrium position. But we don't know the initial velocity of time 0. So that's the velocity immediately after collision that caused the system to move. To find that velocity, we can apply a principle. So these are two particles colliding together. There's no external forces applying, so therefore the linear momentum has to be conserved. So what it means is that we are going to apply the linear momentum conservation principle in order to solve and find the initial velocity. So let's look into that. So we know that the linear momentum principle established that when two particles collide, the momentum is conserved as long as no external forces are applied. So in that case, the equation is of the following form. The initial velocity of mass 2 while it's dropping at a distance from a distant h, that initial velocity is equal to the, and this is the linear momentum of that mass. So that linear momentum before collision is equal to the linear momentum after collision, and after collision, the two masses are attached to each other and has a velocity too. And that velocity is the initial velocity that caused the system to move. So this is going to be equal to V2, and that's the velocity that we are interested. But to get that velocity, we need to find the V1. So how to find B1. To find B1, we can apply the energy conservation principle. So that indicates that energy cannot be created or destroyed. So it means that mass 2 has an original energy before it was dropped, and that's potential energy. When the mass 2 was dropped, that energy was converted into kinetic energy. So that means that the potential energy is equal to the kinetic energy for this system. That applies when a system has no dissipating energies such as friction, damping, etc. Since this system does not have that type of energy, and there's no friction, no damping, we can say that the potential energy is equal to the kinetic energy. So the potential energy of mass 2 before it was dropped is m2gh, and that is equal to the kinetic energy, which is equal to this equation. Now, from here, we know that m's are going to be eliminated, and V1 is going to be equal to the square root of 2gh. So now, we can apply this velocity into the linear momentum equation to get V2. So let's do that. Now, m2 square root of 2gh is equal to m1 plus m2 v2. That coming from this equation, the linear momentum. So this is the linear momentum principle. Now we can get that v2 now is equal to m2 m1 plus m2 multiplied by 2gh, and this is our initial velocity for the, so we can use for the, to apply initial conditions. So now we have two initial conditions. Let's write it again here. X0 equals 0, x dot 0 equals m2, and 1 plus m2 square root 2gh. Okay, now we are ready to use the total solution to get the constants A and B. So let's go back to the equation, the total solution equation, which is in here. So we're going to use this equation and apply the first initial conditions. So it will be like this. X total when time is 0 is going to be equal to A sine 0 plus B cosine 0 plus m2g over k. From this, we can notice that, and I'm going to move this a little bit to the right. I'm going to m2g over k over here. So from this, we can notice that this is equal to 0, the initial displacement. So I got 0 equals to, this goes to 0, sine 0 is 0. Cosine 0 is equal to 1, so we get b plus m2g over k. And then we can find that b is equal to minus m2g over k. Now we can find constant A. Now to get constant A, we're going to take the derivative of the total solution equation at time t. So let's take the derivative. So the derivative of A sine wt is equal to AW cosine wt. The derivative of B cosine wt is equal to minus B sine wt. And then the derivative of m2gk is equal to 0. So this is the derivative of the total solution. Now let's say when x total solution, the derivative, which represents the velocity at time 0, we already determined that that is equal to m2 m1 plus m2 square root of 2gh. So at the same time, we know that, let's write it here, 2gh is equal to this equation. So we know that cosine 0, AW cosine 0 is equal 1 plus minus B sine 0 that we know is equal 0. So now we have m2 m1 plus m2 square root 2gh equals AW. So A is going to be equal to m2 m1 plus m2 square root 2gh over W. But we already identified W at the beginning. We found that W was equal to this value here. So we can substitute into here to get A. So A is equal to m2 m1 plus m2 square root 2gh over the square root of k over m1 plus m2. Now we have the constant A. Now we can establish the total solution of this system. So the total solution was this form. We're going to substitute A and we're going to substitute B on this equation to get the total solution. Is equal to m2 m1 plus m2 multiplied by 2gh and over the square root of k m1 plus m2, and that will be multiplied by sine wt, plus b, which is negative m2g over k multiplied by the cosine wt plus m2g over k. So this is the solution, the complete solution of our system. We can rewrite this equation a little bit further by simply solving for this expression here. So we can have xt equals m2 m1 plus m2 by the square root of m1 plus m2 over k. I simply just did the reciprocal to have the square root in the upper part of it. And that will have the sine wt minus m2gk cosine wt plus m2gk. And that would be the solution for that equation. So I'm missing something here. Multiply by the square root of 2gh in this term. For more content on solving vibrations and control problems, you can subscribe to my channel in YouTube. Thank you.